About the Chiral-induced spin selectivity effect. And for those of you that are not familiar with the effect, the idea is that motion of electrons within Chiral medium, even as small as Chiral molecule, 1 nanometer long, depends on the electron spin. And when I speak Chiral molecules, for the physicists, you have to appreciate that usually we speak about organic molecules, namely molecules that contain carbon and hydrogen. Which spin is preferred depends on the handiness of the system and the direction of motion of the electrons. So basically what we have at end, it's a spin polarizer that can supply us with spin polarized electron on a nanoscale without magnet. And this fact by itself immediately raises questions. How come that we take material that has no spin or very tiny spin orbit coupling, it's so small and so light, no magnet, and we can get up to 100% spin polarization. And that's why, despite the field is now more than about 25 years old, for many people, it's still difficult to swallow the fact that such thing exists. And I will try to go with you and explain to you, first of all, why it exists and how we can understand it in a qualitative way. I'm not going to present many equations. I leave it to Jonas that will give talk tomorrow. He will supply you with as many equations you like. So let's start with a very simple spin polarizer, the Frisbee. When you throw a Frisbee on the wall, we know that if the Frisbee rotates clockwise and the wall is on the right, it will go forwards. If it rotates counterclockwise and we throw on the same wall, it will go backwards. And of course, if we send it to the opposite wall on the left, it will be the opposite. So basically, we have here spin filter. What required to have such a spin filter? First of all, we need the angular momentum, of course. Secondly, we need friction. Somehow, the Frisbee has to communicate with the walls. And the communication is done by friction in the classical way. And if we want to sound sophisticated, we will say in quantum mechanical terms, it's spin orbit coupling and dissipation. And as you will see, actually, this is the essence of spin polarization. So we need two things here. Some interaction that is spin dependent or rotation dependent, and somehow to break space symmetry. Without having both of them, you don't have spin polarization. So when we go to more sophisticated spin polarization, we go to the Mott scattering. Mott scattering, it's really amazing how similar it is to the Frisbee. You take electron, it has a spin, and you scatter it from a gold foil. And what happens there, you find that one spin is scattered in one direction, and the other spin is scattered the opposite direction. And the reason is that spin and the spin orbit coupling of the gold, that's what breaks the symmetry. So this effect is known for almost 100 years. And what is interesting about it, that it's done on macro scale, typically, but it's very effective. Something that's more familiar to most of you is the Rashba effect, and I want to mention specifically a twist on the Rashba effect. It's a work that was done by Finkelstein. He used to be at the Weizmann Institute, and he actually demonstrated how, using the Rashba effect, one can create a spin filter. And in principle, it's the same concept. You have spin and you have special separation. The problematic issue in the Rashba effect that it's based on a band structure theory. So it's very difficult to transform it to something, I would say, macroscopic. But basically, if you follow this line from the Frisbee down to the Rashba, the principles are the same. And here we come to the chiral molecules. Now, look now on the chiral molecules from this perspective. Electron going through chiral molecule must collide with the walls. If this collision is spin dependent, namely there's spin-orbit coupling, and that's another issue, we will discuss it, then it will scatter in certain angle with one spin and different angle with the opposite spin. Since we collect only the population that is scattered in the narrow angle here, we get spin selectivity. And we can think about the molecule as multiple distillation of spin. And basically, it's not so bad because we find typically that the spin polarization increases with the length, linearly with the length. So if we look on chiral system in this way, things look really simple. All what we need, once we have spin-orbit coupling, it sounds obvious. So now when it's so obvious, now the problem is, where is the spin-orbit coupling? Because as I mentioned, spin-orbit coupling doesn't exist in a significant way in hydrocarbon. Okay. Now, the problem is here that the electron going through the system must collide with the system and exchange momentum with the system, very much like the Frisbee. Now, with what the electron can exchange momentum? If we are dealing with a solid, then we have bands. We have delocalized electrons in the bands, and the electron can exchange momentum with these delocalized electrons with no difficulty. However, if we deal with organic molecules, it is a problem because the electrons in organic molecules are localized. Therefore, they cannot take momentum because it required a lot of energy. So with what this electron can exchange momentum? The answer, of course, are phonons, low-frequency phonons. And perhaps I should say it here up front. When I first presented it this way, good and dear theoretician jumped and say, how can it be efficient? You have the mass ratio. So I want to say once forever, collision of electrons with phonon has nothing to do with the mass ratio. this mass ratio comes to us through the Born-Oppenheim approximation, that it's different concept. There we speak about time scale and so on. In collision between electron and phonon, the electron collides with electrons on the system. And these electrons that are on the bonds, they are polarized, they change their position, and that affects the bonds, and that creates phonon excitation. So electron-phonon coupling has nothing to do, in that sense, transferring momentum, has nothing to do with the mass ratio. It's something that I don't know why it's very difficult to get through many of the chemists and the physicists. Okay. So now we see we are facing another problem. We all learn to deal with electron transfer. Typically, when people speak about electron transfer or conduction, they speak about electron transfer on straight line. When you speak about straight line, first of all, you don't have to consider angular momentum or any momentum because it's straight line. And secondly, you know that every interference by phonons or electron collision destroy the conduction. So you want to avoid any interaction with anything. That's the ideal condition for electron motion on straight line. What we see here we see only the electrons that did interact with electrons or phonons. So if you like, it's the complementary population of electrons that you don't see in the regular conduction. So we have to be very careful here, because many things that we learn about conduction are not valid if you speak about conduction through tertiary path like Chiral system. We have to, and especially in this case, we have a problem of momentum conservation, which, by the way, I don't know, most of the physicists are not so familiar with Marcus theory and so on, but the common theories for electron transfer in chemistry don't include momentum. They forget about momentum. And it's clear here that momentum is important. So I think now you realize, first of all, why it's not so simple to model the CIS based on what we knew in the past, because we have to build a new framework, theoretical framework. And this framework has to include two important things. One, its polarizability. When electron collides with an atom, first of all, even if the electron is coming at the Fermi level, it has velocity of about 5 to 6 electron volt. And this electron, when it collides straight on with atom, it polarizes the atom. What I mean polarize the atom? It pushes charge from the atom, electrons from the atom. It's not like pushing charge from an isolated or insulated atom. It's pushing charge into the rest of the molecule, which is much easier. So collision of electron with atoms within material means that there is polarizability effect, and we have to remember that the electron does not interact simply with a closed shell system. The system is never closed shell. The other issue is, of course, dissipation. If we have so many collisions, we do expect dissipation. So only, again, a comment, in linear conduction, we know that dissipation and interaction with phonons are not really efficient, because we look only on the electrons that didn't interact. However, here, it is an important effect. Okay, now, that was something that we could learn simply by looking on the system. We didn't do it. We were not clever enough, and we had to face reality through experiments. That's what's so nice about experiments. Doesn't matter what you think, nature tells you what is correct. So I want to speak first on one type of experiment we did. It's the relation between the spin polarization and the optical activity. Because for chemists especially, when you speak chirality, you say optical activity, because that's the way chemists look on chiral molecules. And it's a property that we think, and I think it's correct, that we understand quite well. We know to calculate it properly, we know what it means. Okay, so here I joined forces with Bert Meyer from Eindhoven, and Bert is expert in making these molecules. Doesn't matter for you the name and so on, but these molecules have here on the side chiral, a group that can be either chiral or not chiral, sorry. Chiral, not chiral, or the opposite chirality. And according to this chirality, these molecules make wires. And the wires are chiral by themselves. So what we did, we take these wires, we put them on the surface. Here we have a magnetic substrate. The molecules are lying here. We come with a tip of a conductive AFM, and we measure the current going between the substrate and the tip, either this direction and back, as function as voltage, as for the two magnetic orientation of the substrate, either when the spin are pointing up or spin pointing down. We can also get the topology here, and so please realize that what we measure is the current perpendicular to the long axis of the wires. And to be sure that we know what we are doing, we measure the thickness of the diameter of these wires, and you see it's a 15 to 20 nanometer. It means that there are many, many molecules that make these wires. And basically, you can look at this as a bundle. Many molecules that organize themselves in a bundle. So it's not simply molecule on top of molecule. Okay. And so we measure the current, and that's what we get. We get different current for the different orientation of the magnet. And then we define spin polarization. People may claim that it's not really the spin polarization, it's the magnetoresistance of the system. I think we have proved that that's correlate very well with the spin polarization, but basically it's the current with spin when the magnet is pointing up minus the current when the magnet is pointing down over the sum. And when we plot it as function of the applied voltage, we get what we call spin polarization or magnetoresistance, and you see here we get 90% for some of the molecule. It's very efficient process. Okay, but then we do something which is the key for this experiment. People that make these wires, it's called in the chemistry supramolecular structure. Many molecules that organize themselves. And these guys know that if they take a chiral molecule and they start to dope it with chiral molecule, the effect on the chirality is not linear. What it means, effect of the chirality? The optical activity doesn't depend linearly on the doping level. And in Eindhoven, they did the measurement, and you see they doped the wire with surgeon are the chiral molecule, soldier are the achiral molecules, and you see in the beginning the dependence of the optical activity is linear on the doping, but then there is amplification and it jumps. That's very well established in supramolecular structure. It's nothing new here. But what's interesting, they sent us for each point the sample, and they asked us to do the measurement for spin polarization. And that's what we got. Fantastic correlation. Now, that's very surprising because optical activity, it's a property of the system. It's not a local property of a point on the molecule. Moreover, optical activity depends on the anisotropy of the polarizability of the system. Basically, it's a result of magnetic dipole times an electric dipole on the system. But it's related to the anisotropic polarizability. So it tells us that the cis depend on the same anisotropic polarizability that optical activity depends on. And that was verified by many groups since then. And it tells immediately that if we want to understand the chiral effect, we must include polarizability. And the polarizability, it's not a property of a point, it's a property of the whole structure. Yeah.
Can you explain how you measure the spin polarization getting up to 100% in this tip experiment?
Oh, we come with a tip.
But where's your spin detector?
What?
Switch magnetization.
We switch magnetization. We measure the current, the definition is the following. The current when the magnet is pointing up minus the current when the magnet is pointing down over the sum. That's it. And it's interesting, it's very robust. The measurements, if you do it in different labs and so on, they agree very well. Okay, so we understand now that this effect, it must involve the polarizability of the whole system. Now we go and shift to another question, because there was a question, what is the role of the molecules and what is the role of the substrate if you have magnetic substrate? So you all know the regular magnetoresistance experiment, where what you do, typically you have two magnets, in between you have insulator. The two magnets, one is a soft magnet, one is hard magnet, and now you change the angle of the magnetization of the soft magnet, and you measure the current with the hard magnet. That's very well-established method, and it works very well. And what you get cosine square type distribution. Okay, we did something similar, but not exactly. We took simple gold, we put chiral molecules. On top of it, we put magnesium oxide layer only to avoid pinholes. But on top, we have a nickel. That's our magnet. So we have only one magnet, not two magnets. And now we change the angle of magnetization of the nickel relative to the current. And what we find cosine square distribution. Now, that's really surprising. Why? Because it means that the molecule behaves as magnet in a sense. It's sensitive, the molecules are sensitive to the direction of the spin. And the question, can we model it? And here again, we went to Jonas. He saves us every time. So he used the model, and you can ask him about the model. The model is simple, but it gives a lot of insight. So first of all, what he did, he take this chain of atoms, and they are sort of our chiral molecules. It's chiral chain, and he has a magnet that inject a spin in different angles, and he measure what comes out, he probe what comes out. So in the first case, he took a system when there is no spin-orbit coupling, neither on the molecules nor in the substrate. And what we see very weak spin polarization, but no angle dependence. Then he put the spin-orbit coupling on the system, only spin-orbit coupling, and then now one gets very weak signal and some angle dependent, but it's not the right angle dependent. In order to get the right angle dependence, you need to put both spin-orbit coupling and phonons that include dissipation. Only if you have them, then you get the right spin polarization. And it's interesting because there were experiments done in parallel, very different methods, both by Angela and Dave Waldeck and Dali in the US, and their results are consistent with this picture. So clearly, I think now we have clear indication what are the ingredients that are required in order to see this effect. Now we go to the phonons. We all learned that if you want to see good conductivity or good spin polarization, cool the system. That's something you learned as an experimentalist on the first day. So here we have the system now. We can measure the spin polarization going through such a system. And I will not go into too many details, but you realize here that the spin polarization increases with temperature. And here it's the Arrhenius plot, and you see clearly that at low temperature here, you have some value up to about 50 K. It's reduced due to regular scattering, and then it jumps up. So above 50 K, we start to get the action. And this could be modeled, and actually it was interesting. Originally, I thought that this has no meaning, really, that it's some, you know, within the noise. But then Jonas came and he got the same thing. And in his calculation, there's no noise. So apparently it's something, and we understand it now. Yeah.
What is the spin analyzer and spin polarizer in that configuration?
What?
Spin analyzer and spin polarizer, and where do you inject the spin polarization? From nickel or from the...
No, we take the current both ways. The current flow either from here to here or from here to here.
So you use the chiral molecule as both analyzer and
Yeah,
polarizer.
right. We always take from, and the plots are not always symmetric, and therefore we present it here in the two directions. Okay. Now we have another system, and this system, this system is special because, first of all, it is a really topological structure, but from the chemical point of view, it has many conjugated electrons. So it means that many electrons are delocalized. And we repeated this type of experiment. We got very nice spin polarization, but then we measure temperature dependent, and you see here the temperature, there is some increase with of the polarization with the temperature, but it's reduced dramatically. And our understanding here that it's a result of electron interaction that takes the role of electron-phonon interaction. So when you, because people try to get an answer, it's phonons or electron? It's both if it's possible. So the system, the momentum is transferred to what is available. And if you have delocalized electrons, they are available, they take some of the momentum, the phonons are much less important here. Okay. So I want to explain, and I follow here again Jonas' direction, how the phonons get in. One explanation, and I think it's very close to reality, is that actually the spin-orbit coupling that we know is not the full story. Because of electron-phonon interaction through a non-adiabatic term, we get enhancement of the field, of the electric field. And this enhancement of the electric field depends on the symmetry of the phonons. And you can see here that the phonon symmetry should be the same as the symmetry of the electric field. Otherwise, things cancel. And basically, this is what we call Chiral phonons, because the system, the electric field has Chiral structure, so the phonons, the momentum must be Chiral phonons. So that's how we relate to this meeting. But it's important to understand that everything we discussed so far points to something very important. We should get detached from Bohr-Oppenheimer approximation, from the single electron picture, and we have to understand that electron correlation are important. So I think that's together, of course, it's a real challenge for calculation, no question about it. But in order to really understand the thesis, that's what we need. Now we go to another effect, time I have, which is perhaps even more surprising than the cis in a sense. And the idea is we put molecules on whole device. Here at least I don't have to explain what is a whole device, not like in the chemistry talks. So we have here a whole device. In this case, it's 2d electron gas system, gallium arsenide, aluminum gallium arsenide, or gallium nitride. We adsorb chiral molecules on the surface. We have a gate here. The gate is either deposited on a dielectric layer, or in some cases, it's in solution. Everything is done in solution. For biological application, for example, it's very important. The gate is insulated from the solution, so no current is flowing, but it applies field. And now we measure the whole signal without applying any magnetic field. There is no magnetic field applied. And we see clearly for this polymer that I showed you before that we put here on the surface, we have for L, we see the whole signal, for D, the opposite for signal, and here you see the whole voltage as function of the gate voltage, and there is clear correlation, and it's opposite for the two Hendenses. Now, it was a big debate. How can we see it? And I think we proved that what we have is anomalous Hall effect. So the idea is that when you apply field on a chiral molecule, you charge polarize the molecule. But when charge is moving, of course, it's spin dependent. So now, at least as a transient, you have spin polarization that's accompanied the charge polarization. In the case of the 2d electron gas, there is an RKY effect that stabilizes these spins, and therefore they are stuck there, and we can measure anomalous Hall effect. But it tells us something very interesting. When the electron moves through such a chiral system, we actually break, at least partially, the entanglement in the singlet state. You know, if you take a chiral molecule or any object, and you excite one side and the electrons are moving to the other side, the electrons are entangled. So you don't know what spin arrived on the other side. Here, because we know what spin arrived on the other side, it means that we broke the entanglement. That was seen also directly in EPR studies. Another thing that we verified with this measurement is that the spins are closely coupled to the molecular frame. You know, in molecules, people do EPR measurements, electron paramagnetic resonance, and the EPR measurements are based on the fact that the electron is not coupled to the molecular frame. So you apply magnetic field, the electron is now aligned according to the magnetic field, but the molecule can rotate freely. Here that's not the case. Here the electron is strongly coupled to the molecular frame because of the strong spin-orbit coupling. So that's something very special, and we break the entanglement. That's also something quite special. So this result means that we have to think on interaction of chiral molecules with matter in slightly different way. For example, when two chiral molecules are approaching each other because of induced dipole effect, there is charge reorganization of both of them. So now they interact, but they interact not only with the charge is accompanied by spin. So one has to include the spin exchange interaction in the interaction, something that chemists didn't do. And Yossi did experiments, beautiful experiment with a tip of an AFM with chiral molecules, and he can measure actually this interaction. And the interaction is between the spin-related interaction is on the order of 100 millielectron volt. So it's quite significant energy, definitely relative to room temperature. The second thing is that now we expect to have a special type of interaction with ferromagnet. I'm not going to elaborate with it, but we use it, for example, to separate enantiomer. We can separate between left-handed or right-handed enantiomer by absorbing them on a ferromagnet. One enantiomer will absorb more with the ferromagnet pointing in one direction, and the other with the ferromagnet pointing in the opposite direction. So there are many implications and application for this effect, and I don't know if Yossi will speak about it, but he showed also that chiral molecules can be considered as magnetic impurity if you absorb them on superconductor. So all comes from this fact that you have spin polarization when you charge polarize chiral molecule. And now I think it will be my last chapter. It's long-range spin transport. I think it's very interesting because it is related to the first talk by Professor Zhang, and you'll see immediately why. Okay, so what we did, we actually deposited here chiral gold. How we make chiral gold? We deposit the gold together with chiral molecules like tartaric acid, and it makes the gold chiral. So you see really spin polarization, CD spectrum of the gold. This is very similar to biomineralization. If you thought why snails are chiral, the reasons that snails are chiral is because in the calcium oxide or silicon oxide, there is doping of chiral molecules. That's the reason. Okay, so what we find here, that for this structure, we can get a magnetic resistance up to about 4.5 micron. So it's really a long-range spin transport at room temperature. The explanation for this is that actually there is spin, of course, randomization, but also spin polarization creation during the motion. And as a result, that's what we get. Here you see a frequency-dependent studies that was done on the same material, and you realize that we can fit it to equations that include build-up and randomization of spin. But what we also get is Hall effect here. Now, this is Hall effect, again, with no magnet. If you remember, Professor Zhang showed you chiral material where there is Hall effect by applying magnetic field. Actually, we don't need magnetic field. What we see here, that we get Hall signal. The Hall signal depends on the enantiomer, if we make a L or D chiral gold. Now, how can we get a whole signal? And that would be a good explanation, I think. So think about our gold. So that's a gold. Let's assume it's closed shell, but it's in chiral environment. Okay, so there is chirality. That's what it means. And we come now with electron, and because of the chirality of the material, this electron now is spin polarized. So what this electron does, it repels charge. It doesn't have to be full electron, but partial charge is repelled from the gold atom into the chiral system. But this charge that's repelled has specific spin. It's the same spin that came here because it has the same chirality. So now this electron interact with open shell, partially open shell, but system with a spin, and now it's scattered. So actually the collision of the electron with the gold created in chiral environment, created the condition for anomalous Hall effect. And all these electrons are scattered in the same direction, and we get the Hall effect. So it's really important to appreciate polarizability takes an important role in all this story. Oh, okay, so basically we can say that this experiment proved that polarizability is important. We get a whole signal with a system with no magnet and no spins. Everything is created during the motion of the electron. And basically, if you think about application, this chiral gold is a good candidate, or not only gold necessarily, but chiral metal is a good candidate for interconnecting spintonics, something that didn't exist. So, where is Chair Lady? I have 5 minutes. Okay, I will take the 5 minutes. So, you know, the big challenge in chemistry is to break symmetry and to make chiral molecules. If you check, many Nobel Prizes in chemistry was given for what's called asymmetric reaction. So you start with material that's not chiral, and you make a material with given chirality. And typically, what you have to do, that was true all the time, you have to use catalyst that is chiral in order to make it. So basically, the question is, can we make the system to go one direction instead of the other direction in reaction without any chiral system? So I apologize for the physicist. Doesn't matter what I show you here. What is important, we start with achiral material, and we make a polymer. Okay, so think about it. We have a building block that's not chiral, and it makes a polymer that's chiral. Now, the polymer that it makes can be either like helix, right-handed helix, or left-handed helix. So what we do the polymerization with spin-polarized electrons. And what we find, here it's the CD spectrum, that for spin pointing to one direction, the polymer shows CD that's going up. In the other case, it's going down. So we make the opposite enantiomer by flipping the spin. How can we understand it? We go back to the Mott scattering. Think about it. Spin is electron with spin coming here. Now the molecule can have the second group here or here in order to polymerize. If we come with the right polarization, it will go here and will make the product. it will not go here. If you come with the opposite spin, it will go here. So based on this smooth scattering that's usually done on macroscopic scale, here within a molecule, we can do smooth scattering and reach product. And actually, there's a beautiful work that was done in China recently, and they really succeeded to make 100% products based on the same concept. It's very, very impressive. So that's what we got. We got either right-handed or left-handed helix based on this. Okay, now I will jump, so go to the conclusion. So important, I didn't go too deep into it, but dissipation is really essential for this process. It cannot exist without the dissipation. Polarizability plays an important role. And here I want to make a comment. We see, that's something I skipped because of lack of time. We see the effect, the cis effect in proteins. And we see there the effect polarizability. And immediately I was asked by the biologists, how come you see effect polarizability in protein? Is it not screened, the field? So we did quickly the calculation. The polarizability of protein is about 10. And when you calculate the screening length of protein, it's exactly the size of the protein. So polarizability in protein means that if the protein feel electric field or electric potential, it will be polarized all through the protein. And that's really important finding. Okay, the effective spin-orbit coupling is not the simple atomic spin-orbit coupling. Now we're finding more and more things into this spin-orbit coupling. It's really fascinating subject, and I hope very soon we will come with even more exciting results about it. Angular momentum consideration must be added to all the calculations for electron transfer. And right now, there are the group of Joe Subotnick that developed actually ab initio calculation that are non-Born Oppenheimer and conserve momentum. So it's really very interesting breakthrough. And we can have really long-range spin transport at room temperature using this cis effect. Okay, thank you very much. Here are the people that did the work. These people with the red circle current group, some are living, and thank you very much.